Hello everyone, welcome to my presentation. The presented paper entitled Efficiency of Precast Concrete Tunnel Lining Segments Reinforced with Gfrp Bars Under Bending Load. In my presentation, I'll start with introduction, and after presenting a literature review and research significance, I spend some time on experimental work and experimental results and discussions, and I'll finish with conclusion. In mechanically excavated tunnels using tunnel boring machine, the precast segments ring sequentially placed as the tunnel drilling advances. And each ring comprises from a certain number of segments, defining a multiple joint structure. Traditional types of PCTL segments were steel reinforced one, which suffers from corrosion problem. This corrosion problem is very major in the tunnels because of presence of underground water and aggressive soils. And also in metro tunnels, the estuarine current makes this degradation more severe. An effective approach to mitigate this problem is using Gfrp bars as a replacement of steel bars in tunnels. Gfrp bars are resistant against corrosion and chemicals, and they have electromagnetic neutrality, which is important in metro tunnels. They have high strength to weight ratio, high tensile strength, competitive life cycle costs, and they are resistant against fatigue. Also, the concrete cover can be reduced with using such reinforcement in the tunnels. A reduction of concrete cover is very beneficial because the excavation cost can be reduced, and also they are suitable for parts of the tunnels that should be demolished after construction because they easily can be cut. The first study that used this type of reinforcement in tunnels was in 2016, where Carter et al. Compared the performance of Gfrp reinforced and ST reinforced tunnel segments using flexure and truss tests, and designed the segments to have almost the same capacity. But they use a smooth Gfrp bar in the specimen. They observed a bar rupture failure mode, and they concluded that the flexural behavior of these segments are not very different, but the reported crack width at service load was higher than the allowable crack width in the standards in Gfrp reinforced segment. In 2017, Spagnolo et al. They obtained the theoretical design PM interaction using ACI 440 for Gfrp reinforced tunnel segments, and they concluded that the simplified check procedure for tunnel segments based on the presented model is suitable to predict the load carrying capacity of the segments. In 2017, Karateri et al. They investigated the effect of different configurations of Gfrp reinforcement on the behavior of Gfrp reinforced PCTL segments, and different types of ties and configuration were introduced, and the performance of sand-coated Gfrp bars was also compared with the specimen with smooth bars. They concluded that a closed ring reinforcement, which is a closed in all direction, is the best prototype tested, and also the coating treatment based on the results improved the cracking behavior by 70%. There are very limited studies in the literature regarding to the Gfrp reinforced PCTL segments. I can say that less than 10 specimens were tested, and the observed failure mode in the specimen was tension bar rupture failure, which is unfavorable according to the design standard, and the smooth square bars was used in majority of the tested specimen in the literature, which is not recommended by the design standards. And we can say that the efficiency of Gfrp reinforced PCTL segment needs much further investigation before major application in tunneling projects. In this study, the behavior of a Gfrp reinforced and a ST reinforced PCTL segment with identical geometry and details are compared, and they utilized Gfrp curvilinear bars, were sand coated and produced with new manufacturing process with improved properties. And the Gfrp reinforced specimen is designed in such a way that it goes to experience compression failure mode, which is favorable. I can say that it is a part of a very great research project at the University of Sherbrooke, and I only present a very small part of the preliminary results in this paper. Uh, each segment comprised from a longitudinal top and bottom bars and the closed and the transverse ties. For the longitudinal bars, number 5 curvilinear bars with a specified radius for bottom and top mesh was used. And the end anchorage U-shaped bars were used to provide end anchorage, and the closed Gfrp number 4 ties were used as a transfer ties. The test specimens was a full scale with arc length of 3100 millimeter, and the specimens were parallelogram in the shape. In the Gfrp reinforced and ST reinforced segment was identical with 7 bars in each mesh. And also everything was identical in these two specimens. And here is the Gfrp reinforced specimens placed inside the formwork, and here is the casting procedure. 3-point load test setup was used for testing of the specimens because cracking investigation is easier and better in 3-point load test setup, and it is more reliable due to the curve shape of the segments, and this is what also used in majority of the previous research in the tunnel segments. The ST reinforced and Gfrp reinforced specimens followed a typical flexural behavior with appearance of flexural cracks, and after that, in ST reinforced specimen, after yielding of reinforcement, the concrete crushing happened, which denotes the tension controlled fracture failure. And the Gfrp reinforced specimen also failed by concrete crushing, which is a favorable failure mode in Gfrp reinforced flexural elements. The ultimate load in Gfrp reinforced specimen was higher than the ST reinforced one, and also the ultimate deflection. Here, the load deflection relationship is presented. As you can see, the ST reinforced specimen followed a typical steel plateau. It goes after cracking to the yield, and after yield it goes with the concrete crushing, which happened in 3 stages. The Gfrp reinforced specimen, after the cracking, it followed a linear behavior until the failure, with higher load carrying capacity and higher ultimate displacement, which shows a good deformability of these segments. And also the from the test observations, the cracking at service load and the deflection satisfied the design criteria of the design standards. The post-cracking stiffness of ST-reinforced specimen was higher than Gfrp reinforced was, which was predictable according to higher module of elasticity of steel bars. But the module of elasticity of steel bars was around 4 times higher than the Gfrp bars, but the stiffness was only 2.7 greater. It shows that the Gfrp reinforced specimen also can meet the requirements regarding to the deflection behavior. We can conclude that the failure in Gfrp reinforced specimen governed by concrete crushing and the tension control flexure failure observed in steel reinforced specimens. The ultimate load carrying capacity of Gfrp reinforced specimen was 33% higher than the steel reinforced one, with having the same reinforcement detail. And the Gfrp reinforced specimen showed a linear elastic behavior until failure. Can say that application of Gfrp reinforcement in PCTL segment is an effective approach to deal with the corrosion problem and to take advantage from unique feature of Gfrp bars and tunnels. And Gfrp reinforced PCTL segments showed a satisfactory structural performance under bending load regarding to failure mechanism, ultimate load and deflection, service cracking, and deflection. At the end, I would like to greatly appreciate the funding agencies and industrial partners for their valuable support in this study. Thank you so much, everyone.